Berlin, a vibrant metropolis. Reliable mobile telecommunications are essential. The future is UMTS, Europe's third-generation telecommunications technology. The new technology enables faster and more efficient communications. More information can be transmitted in less time. This is realized by a new generation of radio equipment. The antennas have to be combined to an efficient radio network. This problem can only be resolved with state-of-the-art mathematical methods and software. Scientists at the Research Center Matheon in Berlin have taken up this challenge. The basis for their work is data on propagation of the radio signals emitted by an antenna. Predicting signal strength in urban areas is especially difficult, as signals are diffracted and reflected by buildings. With the new technology UMTS, all antennas transmit in the same frequency band. The radio frequencies are utilized more efficiently, but radio network planning is more involved. Each antenna serves a certain area called its cell. The problem? At the cell's periphery, signals interfere heavily. In busy areas where many people use cell phones, many antennas are present. They have to be attuned to each other in order to achieve good service, especially in a big city such as Berlin. The prerequisite for this is a detailed analysis of the radio network and the coupling between cells. Researchers at Matheon work with huge amounts of data. The data is analyzed with tailor-made computer models to detect the main source of problems in the radio network: interference. Interference can spoil the mobile phone experience. Interference becomes tangible when the user enters an area with several sources of interference. Then a critical interference level is reached. The connection might break down or fail to be established in the first place. Matheon scientists are striving to resolve this problem. Their task is to avoid troublesome interference wherever possible. Their mission is to optimize the network such that it works smoothly everywhere. Only then can new services like video telephony be fully enjoyed. This state-of-the-art mathematics addresses pressing needs. The computer programs developed by the Matheon scientists determine an optimal configuration for each antenna. Technicians implement the radio network design. The result? The red areas with high interference are diminished and do not compromise network operations anymore. Innovative mathematics enables an unlimited mobile experience. For getting around a city like Berlin, the subway is the best choice. To reach their destinations, more than 80% of all passengers need to make a connection. That's where people have to wait the longest, every day. In the most annoying case, passengers narrowly miss their connecting train. Who wouldn't want a better connection?
Es ist jetzt keine Verspätung der Züge. Es handelt sich hierbei wirklich darum, dass es im Fahrplan so aufgebaut ist, damit jeder...
In the evening, this amounts to a wait of up to 10 minutes. What would a better schedule look like? Consider this. These passengers just barely missed their connecting train. The next one will not arrive until 9 minutes later. This happens again and again for every train. Let us change the timetable to reduce the waiting time. We delay the blue train ever so slightly, so that connecting passengers at our current station won't have to wait. But now other passengers will miss their connection. We change the schedule once more, and once again we create problems elsewhere. Ultimately, we end up changing the schedule of the purple train, so that we haven't gained anything. Some delays are unavoidable. In the real world, the problem becomes even more complex. As many as 170 connections need to be coordinated if more than 1 million passengers per day are to reach their destination quickly. This was the challenge for the Berlin subway. Their chief planner teamed up with mathematicians of the research center Matheon. Short waits were not the only goal. Further conditions had to be met. For instance, waits at this station must be avoided no matter what. Even in areas that no passenger will notice, intelligent planning is a necessity. At this terminal, incoming trains must clear a switch before departing trains are allowed to leave. Matheon researchers have developed techniques to solve this difficult problem. Each point in this animation represents a subway schedule that's possible in theory. The number of possible schedules exceeds the number of atoms on our planet. Even the fastest computers cannot check all the schedules. Only mathematics is capable of ruling out entire sets of unsuitable timetables at once. Once a practicable schedule, highlighted in green, has been found, the resulting weights are calculated. Better schedules eliminate inferior ones, highlighted in red. Again, entire classes of unfavorable schedules are ruled out. Eventually, such techniques find the best timetable for the given set of constraints. Ultimately, the members of the Combinatorial Optimization and Graph Algorithms group at TU Berlin were able to turn these mathematical ideas into real-world technology. Since 2005, the Berlin subway has been operating on a provably optimal schedule, designed by Matheon. The facts. The average waiting time went down from 2.48 minutes to 2.5 minutes. The percentage of fast connections went up from 55 to 60. The maximum stopping time has been reduced from 3.5 to 2.5 minutes. And finally, the schedule can be operated with 1 train less. Mathematics saves us time. Sometimes it even makes us happy. Because there are better ways of spending your time than waiting for a train. Walking. It looks so simple, and yet is physically so demanding. Intellectually as well. To collect the necessary movement data, and from them to calculate the stresses and strains in the knee joint with all the bones, muscles, and ligaments, is for physicians and mathematicians a real challenge. Fine if everything is running smoothly. But not so fine when an operation turns out to be necessary and the bone has to be repositioned. A fascinating question not only for surgeons, but also for mathematicians. How must bones, ligaments, and muscles be positioned during an operation in order to restore a knee's entire functionality? Even small malpositions may lead to undesirable restrictions of movement and to unbearable pain. Ideally, the surgeon would like to see already before his intervention how the knee will function after surgery. For this, he needs the mathematician. In Berlin, mathematicians of Matheon and physicians of Charité have been collaborating on this topic for several years. One difficulty is that no two knees are the same. Another is the movement of the knee is highly complex. In the gait laboratory of Charité, high-precision measurements of individual patients' movements are presently being performed to gain a better understanding of this. At the same time, mathematicians generate individual 3D knee models, which serve as a basis for computing stresses in joints. For this purpose, highly complex systems of equations with many thousand unknowns have to be solved both fast and reliably. Following the principle of divide and conquer, these systems are decomposed into a hierarchy of subproblems and, by means of convex analysis, then recomposed. The result? Monotone multi-grid methods which supply the solution after only a few steps. How do changes to individual parts of the knee influence the total load? What happens during the processes of walking, stair climbing, or long jump? In the orthopedic virtual lab, all these questions can be tackled without any danger or pain. Repositioning the insertions of tendons or removal of a cruciate ligament. At Matheon, new sophisticated mathematical knee models and algorithms are being developed that should improve the planning of medical interventions in the near future. Well before the surgeon takes up his scalpel, he can picture the various operation scenarios in the virtual orthopedic lab, with the aim of avoiding discomfort for the patient in the long run, and thanks to a mathematical look into the future.
Wow, he sure has to deliver a lot of papers. Almost every house gets one. I wonder how he decides which route to take. Like the garbage collectors, they must plan as well, and gas prices are rising all the time. You can save a lot if you plan before you go, but how do you handle problems like this at all?
The key concept is route planning. It's also important for tourists in a foreign city. However, what's the best way to get from A to B can determine success or failure in business life. You don't find the answer by trial and error, but by using mathematics. Within the DFG Research Center Matheon, mathematicians are working on optimizing traffic networks. They want to know how to find the cheapest, fastest, or most pleasant way between two locations. The biggest challenge? Finding an optimal schedule for a complete network. Discrete mathematics plays a key role. The models that are developed there solve these kinds of problems. Problems that not only fascinate mathematicians, but school students as well.
Der Schüler, der steht hinter der Tafel. Hier ist die Tafel, da steht der Schüler dahinter.
Complex mathematics that students enjoy. For the scientists in the education area of Matheon, this is not only a desire, but everyday work. How can a child best understand complex mathematical problems? Which methods can a teacher employ to get complex issues across? Matheon mathematicians are looking for new ways. Their main goal? Showing students that mathematics plays a role in almost all areas of life, and that designing models is thus an important skill to have. Sensible use of computers is a focus of the researchers. Within the Matheon project Visage, activities and interactive computer software is developed. Hands-on mathematics. Educational games actively facilitate understanding. The concrete problems are within the reach of the students' personal experiences. Students learn how proper modeling and planning can help find an optimal solution more easily and efficiently. Yet first, teachers must learn these new topics and methods as well. Due to efforts of Matheon scientists, the school curriculum in Berlin will contain discrete mathematics for grades 7 through 10, starting with the school year of 2006. In Berlin, teachers can learn about these exciting new developments in their own schools in teacher training courses. Not only Berlin's students profit from improved mathematical comprehension, the foundations are laid in the schools. Then, more difficult challenges can be met later on. Thus, discrete mathematics helps you reach your goals faster.
Remember, for problem B, apply the chain rule. And don't forget, in doubt, everything can be rederived from the definitions.
What is differentiation? A particularly tedious exam? With a complicated set of rules? A mess of formulas which drive some people crazy? Longings emerge which have absolutely nothing to do with mathematics. One might be tempted to ask in this situation, what do we have computers for? The derivative of a function represents the slope of its graph at a point. Already at the turn of the first millennium, Indian mathematicians knew about complex trigonometric functions and approximated them by tangents, parabolas, and cubic polynomials, which can be constructed using derivatives. In the 12th century, the Arab mathematician Al-Tusi used such polynomial approximations to look for optima, the exact point at which the derivative vanishes and the tangent is thus horizontal. Invented some 800 years ago and still of great interest today.
So this is the fixed point iteration that we're trying to stabilize.
Worldwide, mathematicians still work with these tools, only some names have changed. Now we talk of the Leibniz rule and Newton's method. They are indispensable for solving computational tasks of everyday life. For example, the determination of optimal values for performance indices that measure the efficiency of complex technical devices as a function of their design. This works, for instance, in the layout of traffic networks or the design of airplanes, up to the planning of entire industrial plants.
We aim at the development of efficient airplanes, and there the primary goal is the reduction of the air drag. Here we see the drag coefficient of a sailplane as a function of the wingspan. To minimize it, one needs to find an optimal trade-off between two countervailing effects, namely the induced drag and the profile drag. Exactly where the slopes of these two drag curves cancel each other, one finds the minimum of the total drag. Dr. Holighaus observed these curves some time ago and designed correspondingly optimized airplanes, like, for example, this Nimbus 3. For larger airplanes, one uses complex computer codes to simulate their properties. To optimize, we first need to differentiate. This differentiation follows the familiar rules, but we have adjusted them a little bit to make the whole process more efficient. Here's the result of automatic differentiation, a compact sequence of instructions which allow effective optimization. Naturally, we still need practical testing and experiments.
Flight pioneers of days gone by often put their lives on the line. Today, we can be a bit more cautious.
Here, the hobby designer struck it lucky. This is an aerodynamically adequate design with stable flight characteristics. Obviously, we no longer design by trial and error, but employ mathematical simulations. Naturally, many side constraints need to be taken into account. For example, that we can carry loads, like kerosene, cargo, passengers, that would clearly be impossible here. To define these side constraints appropriately, we need the collaboration with engineers, and hence the Humboldt University cooperates with the German Center for Air and Space Flight.
Together they work on CAD models of a passenger plane with several million grid cells. This creates a system of several million equations which describe the flow around the aircraft. The derivatives of these equations indicate in which direction one must search for the optimal aircraft shape. In this way, one ends up with not just one, but millions of tangent slopes. They all must be brought down to zero during the course of the optimization, a condition for optimality. Naturally, none of this is done by hand, but with the help of highly complex differentiation and optimization software, developed over the last years through the collaboration of mathematicians of the Humboldt University and scientists of the German Center for Air and Space Flight at Braunschweig. Up and away, through differentiation and optimization. So the tedious exam question turns into an adventure tour through unexpected territory. In this way, mathematicians can cause butterflies in your stomach. Lots of noise on the street and inside the car as well. This is annoying for the driver and interferes with more pleasant sounds. What a pleasure it would be to simply switch off the noise. But it's not as simple as all that. Noise comes from everywhere and is amplified. A disturbing concert with many unknown artists. The reason? Vibrations of individual car components. They are set in motion even by weak outer forces. You can hear the results, just like a violin. While the little violinist needs the vibrations of the strings and the resonance of the case, car designers want to detect and prevent such vibrations and resonances. This, however, is not done on the test track, but by numerical simulations in the computer.
SFI Akkusmod berechnet den Weg von der schwingenden Blechstruktur.
SFI Akkusmod computes the path from the vibrating structure to the noise the driver hears. In the animation, we see the structure of the car oscillating with 57 oscillations per second. Mathematical algorithms help to compute the noise level produced by the oscillating structure. With our program, we can detect the parts of the car that contribute most to the noise. The designers in the automotive industry can then systematically improve these parts.
The mathematical foundation is very simple.
Emma, imagine, Catherine and Emma together are 39 years old. And Catherine is 15 years older than Emma. This is what the second equation means. How can we compute the solution?
I don't know.
We add both equations. Catherine plus Catherine makes 2 times Catherine. Emma minus Emma is nothing. And 39 plus 15 is 54. How old is Catherine?
Wie alt ist jetzt Katrin? 27.
Exactly. And in the same way we can solve this for Emma. We subtract the second equation from the first and get 2 times Emma is 24. How old is Emma?
12.
Emma ist gleich 12.
I knew that.
Mathematicians write these systems of equations in a simpler way. We only take the numbers. Instead of the k and the e, we just write 1. And here we have 1 in front of the k and a -1 in front of the e. We put the numbers here and the 39 and the 15 as well. And the object here we call a matrix. Here we have a very big matrix. These are more than 100,000 entries. And the black dots that you see are all unknowns. Emma's, Catherine's, Thomas.
Quite a lot.
Based on such simple computational steps, one can develop powerful mathematical methods that can solve equations with millions of unknowns very efficiently.
A few years ago, the solution of equations with millions of unknowns would have been impossible. But the drastic improvement of computers, here shown by the green curve, and in particular the even more drastic improvement in the mathematical methods, here shown by the red curve, now allow to solve systems with millions to billions of unknowns in seconds to minutes.
The solution of huge linear systems is one of the building blocks in the noise optimization program of the company SFI.
For the acoustic design, we need an accurate model of the car. In SFI concept, the whole structure is kept in the computer in a parametric model. In this way, we can move a part, like the crossbar here, in an arbitrary way and obtain a computable geometry for every state. The program makes sure that all parts are correctly connected. They are connected via weld points. In a computer simulation, one can now move the crossbar into different positions to find the optimum.
so das Optimum zu finden.
What previously was done only by trial and error is now improved virtually in the early planning process by solving millions of equations. Less noise is good and allows the unexpected. From the back seat. Provided the peace is not disturbed.
Blut. Nicht nur für Kriminalisten ein interessantes Untersuchungsobjekt. Auch Mediziner sind daran interessiert. Vor allem an bestimmten Bestandteilen des Blutes, den Eiweißen. Die eigentlichen Täter, denn sie spielen bei der Entstehung zum Beispiel von Krebs eine entscheidende Rolle. Die Spurensuche im Blut beginnt. Nach der Aufbereitung des Blutes im Labor wird das fast durchsichtige Blutserum zur Analyse auf den Trägerchip pipettiert. Gebraucht wird dabei viel Licht. Laserlicht. In diesem Massenspektrometer wird der Bluttropfen damit beschossen, um die darin enthaltenen Informationen sichtbar zu machen.
Die Probe wird mit einem Laser beschossen. Die Proteine werden dabei in die Gasphase überführt, ionisiert, in einem Hochspannungsfeld beschleunigt. Sie fliegen nach oben zum Detektor und werden dort anhand ihrer Flugzeit gemessen.
Das alles geschieht in kürzester Zeit viele tausend Mal. Die geladenen Moleküle, jetzt in der Gasphase, werden durch ein elektrisches Feld beschleunigt. Je leichter die Teilchen, desto schneller fliegen sie. Durch die gemessene Flugzeit können nun die einzelnen Massen berechnet werden. Viele tausend Teilchen reagieren auf diesen Lichtbeschuss. Und das alles unter schärfster Beobachtung. Dabei sind jedoch nur weniger als 100 Täter interessant. Und diese gilt es zu finden. Die entscheidende Frage, wo verstecken sie sich? Denn die Informationsmenge ist fast unüberschaubar. Für die Labordetektive aus alten Tagen eine unlösbare Aufgabe. Die Daten von nur einer Blutprobe füllen eine ganze DVD. Zur Analyse wird dieser Datensatz nun von Dr. Tim Konrad, Wissenschaftler am Mathematischen Institut der Freien Universität Berlin und dem Matheon, bearbeitet. Welche Analysemethode verspricht nun die höchste Effektivität? Wie kann die Spurensuche beschleunigt werden? Eine Analyse-Pipeline mit einer Reihe von neuen Algorithmen ist der Schlüssel für eine erfolgreiche Täterjagd. Der Prozess beginnt mit den Rohdaten aus dem Massenspektrometer. Diese werden entrauscht, um die nachfolgenden Schritte zu erleichtern. Danach wird die Baseline herausgerechnet, die durch das Massenspektrometrieverfahren verursacht wurde. Zudem werden die Spektren auf ein vergleichbares Niveau normalisiert. Nun werden in dem geglätteten Spektrum die eigentlichen Signale, die Peaks, identifiziert. Dazu werden mögliche Start- und Endpunkte gesucht. Oftmals überschneiden sich auch mehrere Peaks, deren ursprüngliche Form dann rekonstruiert werden muss. Ist ein einzelner Peak gefunden, werden seine Eigenschaften wie Position, Höhe und Fläche analysiert und gespeichert. Im nächsten Schritt legen die Forscher die Spektren von unterschiedlichen Patienten mit der gleichen Erkrankung übereinander. Gesucht wird dabei nach sogenannten Master Peaks. Das sind Peaks, die in allen Patientenspektren gleichzeitig vorkommen und ähnliche Eigenschaften haben. Die Eigenschaften der gefundenen Master Peaks werden mit den Daten von gesunden Menschen verglichen. So können krankheitsspezifische Merkmale bzw. Unterschiede identifiziert werden. Die Kombination aus besonders deutlichen Unterschieden liefert den Forschern für diese Krankheit einen Fingerabdruck. Dieser kann bei der Spurensuche im Blut entscheidende Hinweise liefern und den Täter überführen. Alles deutet darauf hin, dass dieses Protein, zum Beispiel bei einer Krebserkrankung, eine wichtige Rolle spielt. Diesen Fingerabdruck, typisch für Prostatakrebs, kann Tim Conrad nun gezielt in Blutproben von Patienten suchen. Mit den bisherigen Rechnern eine zeitraubende Aufgabe. Stärkere Rechner gibt es, doch die sind teuer. Für eine Routineuntersuchung unmöglich. Hilfe kommt von unerwarteter Seite. Was virtuelle Helden zum Leben erweckt, kann auch bei der Blutanalyse helfen. Die guten alten Zeiten gehören der Vergangenheit an. Mit den neuen Algorithmen, die auf dieser Playstation laufen, sind die Forscher wesentlich erfolgreicher auf Verbrecherjagd. Ihre Hightech-Lupe vergrößert bis zu 250 Mal stärker als die Software in den bisherigen Laborgeräten. So kann das Blut eines Patienten jetzt genauer und schneller nach den üblichen Verdächtigen durchsucht werden. Und noch etwas rückt in greifbare Nähe. Da man nun den Fingerabdruck einer Erkrankung kennt, könnte es zukünftig möglich sein, spezifische Medikamente zu entwickeln, die die krankhaft veränderten Proteine im Körper gezielt bekämpfen. Das Medikament nach Maß.